I hope everybody hears me fine and the slides are visible. Okay, good. So as Anand mentioned, I'll talk about spectral clustering oracles, basically graph clustering in sublinear time. And please do stop me at any time if anything is unclear. I intend to. The hope is that everything is clear. Good. So this talk is about graph clustering. And well, what is the task in graph clustering? Well, the goal is to take a graph, G, such as the graph shown on the slide, and partition the vertices of the graph into non-overlapping sets, C1 through Ck, where K is the number of clusters that we're looking for, such that somehow every set Ci is a community of sorts. Okay, so here's an example of an input graph on the slide, and here's a pretty reasonable solution. We can partition it into clusters C1, C2 through C3, shown on the slide. Good. So clustering is, of course, a basic primitive in graph analysis, has numerous applications, which I will not dwell on here. Good. So in this talk, we are interested in finding clusterings of graphs that actually admit good clusterings. We'll be interested in very fast algorithms for this problem. So in what follows, I will start by defining the class of input instances that we're interested in. So we call those clusterable graphs. Then I'll talk about what was known before about this clustering problem, and finally get to our main result. Good. So what are clusterable graphs? Before I tell you what clusterable graphs are formally, I need to define what I mean by a good cluster. So here's an example shown on the slide. What you see on the slide is a subset C of vertices in some bigger graph. So there are 5 vertices here, and note that there are some edges that go to the outside of this cluster. In this talk, well, first we assume that the input graph is deregular for some D, and we define the conductance of a cut S to C minus S inside a cluster C, so this cut is shown on the slide, as follows. Well, it's the standard definition of conductance, and it's nothing but the number of edges crossing the cut, normalized by the total degree on the S side of the cut. And here we're thinking of S as being at most 1/2 of C, 1/2 of the size of C. Okay, good. So the conductance of a cut S inside a cluster C is nothing but the number of edges crossing from S to C minus S, normalized by D times S. Again, think of S as the smaller side of the cut. Great.
So Michael, here, C is not necessarily all the vertices of the graph.
Exactly, yes, excellent point. So yeah, so C is some subgraph, sort of vertex-induced subgraph of the input graph. Yeah, exactly. So note that here we are normalizing, so our notion of conductance is the number of edges crossing the cut, normalized by D times S. So the graph is deregular, so in particular, we're basically normalizing by the original volume in the graph, not by the volume in the subgraph. Right, so these edges that go to the outside that are shown as sort of bluish here, they do contribute to the denominator. Yeah, excellent point. Good. Good. So now the inner conductance of a cluster C, denoted by phi in of C, is nothing but the conductance of the least conducting cut in this subgraph C. So here we just take the minimum over all S that are at most 1/2 of the vertices. Okay, great. So intuitively, right, a cluster C that has high conductance forms a good community. It's well connected. Good. So now what is the outer conductance of a cluster C? So this is denoted by phi out of C. Well, it's nothing but the conductance of the cut induced by C in the basically it's nothing but the number of edges that go from C to outside of C, normalized by D times the number of vertices in C. All right, good. Are there any questions about these definitions? Okay, if everybody is happy, then we basically can now define what we mean by a valid cluster. So what is a valid cluster for us? It is just a vertex-induced subgraph C of the graph G with inner conductance at least phi in for some parameter phi in, and outer conductance at most phi out. Okay, and these two parameters will stay with us for a few slides. Basically, you should think of phi out as being significantly smaller than phi in here. So we want well-connected communities with a pretty sparse boundary. Okay, so just as a small detour, which will be important in what follows, recall that this notion of inner conductance is related to the eigenvalues of the normalized Laplacian through Cheeger's inequality. Specifically, we can bound the second eigenvalue of the normalized Laplacian of this subgraph C, induced by vertices in C, by as a function of phi n. Basically, the second eigenvalue is at most 2 lambda, so at most 2 phi n, and is at least the square of phi n with a constant. Good. So in particular, what we know, and this is something that we will use, we know that in a graph with inner conductance at least phi n, random walks mix in at most order log n over phi n squared time. Basically, they mix to the stationary distribution, and which here is just the uniform distribution, because the graph is regular. Okay, great. So equipped with these definitions, I can actually tell you what clusterable graphs are. So graph G is called K phi in phi out clusterable if there exists a partition of the vertex set of G into sets C1 through Ck, such that every cluster, we'll call these CIs clusters, such that every CI has inner conductance at least phi in and outer conductance at most phi out. Furthermore, in this talk, we will assume that all the CIs are of size omega of n by k. So there sort of think of them as being roughly comparable size, right? Yes, exactly. So there's k of them, so there should be about n by k. So here's an example that we started with. This is a clusterable, 3 clusterable graph with some reasonable parameters phi in and phi out. Good. So just to avoid complicated notation, in what follows, I will focus on graphs that are omega 1, epsilon clusterable. So basically, what is called phi in, I will just set to some absolute constant, and for the outer conductance, I will have a parameter epsilon, which is small. So you should think of epsilon is as smaller than a constant. Okay, great. So this is really the question that we would like to ask in this talk. Suppose that our input is a k omega 1 epsilon clusterable graph. That is, it's a graph that can be partitioned into k roughly similar size pieces, with each of which is a good expander, and each of which has outer conductance bounded by epsilon. So the boundary has sparsity at most epsilon. Great. So here's the example on the slide again. And what we want is to design a very fast, design a data structure that provides a fast query access to this partition into C1, C2 through C3. Okay, of course, we can't really get the exact partition. So instead, we're asking for a data structure that allows fast query access to a partition C1 hat, C2 hat through Ck hat. And we want this partition to approximate the original partition well. What does that mean? Well, we want what we call per cluster error of order epsilon. So what does that mean? This is shown, formally stated here in the slide. We want that for every I from 1 to k, the symmetric difference between the ith cluster and its approximation C hat is order epsilon times the size of that cluster. Okay. Basically, they have to have very good overlap. The approximate clusters have to be have very good overlap with the individual clusters. Okay.
Yeah, quick question. So the 2 epsilons are the same, but they can.
Yes. Oh, great question. So Siddhartha is asking, look, we have the epsilon in the definition of a clusterable graph, and then we have this epsilon in the, which is a precision parameter in our procedure. Is it meant that they are the same, right? And the answer is yes, it is meant that they are the same. And here one could ask the question of trying to recover this partition C1 through C2 through C3, let's say to a better error than epsilon. Right? One could imagine having some epsilon prime, but actually this is just not possible for the following simple reason. Suppose that k is 2, imagine the following. Do the following: create a graph with n by there's just a disjoint union of two good expanders. Okay, and then do the following: you add an epsilon fraction of vertices that have half of their connections, say, randomly to the first expander, and half of their connections randomly to the second expander. And then, well, this graph is k is 2 omega 1 epsilon clusterable. However, the clustering is not unique. So in general, given a clusterable graph, you can find a bunch of different clusterings. So in this case, you look at these middle vertices, and you can either put them on the left or on the right. You still get a valid clustering. So it's just information theoretically impossible to get these clusters up to error better than epsilon. Yeah. So great question.
And just for my understanding, like the definition of clusterable is like one way to probably see it is that you have k expanders that are sort of connected somehow. So this is like
exactly. Yeah, think of it, basically this is k good expanders that are loosely connected, right? But and the loosely is quantified by epsilon.
And it's a promise problem. Like
exactly.
The goal is not to like test whether the input satisfies this property, but to just assume it.
In this talk, I assume this, but I'll talk about the promise, the testing in just a second. Yeah. Okay. In this talk, our input is a clusterable graph. Okay, great. So, okay, good. So let's see if there are more questions. Because, so again, basically our input is a graph that is a union of k good expanders with epsilon-sparse boundaries, and we want a data structure that allows fast query access to an approximate partition. Right. Yeah. And by the way, so here I would like to stress that this fact that we're insisting on per cluster error of order epsilon is actually very important. You could ask the following question of whether we can get a data structure that misclassifies only an order epsilon fraction of vertices, as opposed to misclassifies an order epsilon fraction of every cluster. And so this second question is significantly easier. So in particular, you can say misclassify an order epsilon, and you can ensure that you misclassify an order epsilon fraction of vertices without even outputting a partition into k clusters. You could have just fewer clusters. Yeah, so this is very important. Okay, great. So let's see how would we solve this problem in general? So what is known about such problems? Okay, so for cluster recovery, first thing that one can apply is results on multi-way Chigurh's inequality. Right, so for example, the ones from James Lee, Cheyenne Weiss-Garan, and Luca Trevisan. So here we would need the outer conductance to be inverse polynomially small in the number of clusters, and the misclassification error would be some poly k times square root of the outer conductance. Good. There's a very nice paper of Ali Sinop from SOTA 15 that solves this, that allows recovery of clusters up to error square root epsilon. And so this works all the way up to epsilon, a small constant. So this will be a bit more relevant to our work. Both of these results run in time nearly linear in the, size of the graph times poly k. Good. But in this work, we're interested in sublinear time algorithms for this problem. So basically, we don't even want to read the entire graph. Good. So now, what is known about solving such problems in the sublinear regime. Okay, so first, so here most of the work has focused on the property testing version of this problem, and really this line of work started with the work of Goldreich and Ron, who considered the expansion testing problem. So the expansion testing problem is really the problem of distinguishing between graphs that are a graph that is an expander versus a graph that has a sparse cut. So you can think of k equals 2 here. Okay, so Goldreich and Ron proved that any algorithm that distinguishes between these two cases requires omega square root n probes. The sample complexity is at least omega square root n, and hence the runtime is at least this much. Then Kali and Seshadri proved that you can solve this problem for any epsilon smaller than a constant in time n to the 1/2 plus order epsilon. And reasonably recently, so this is Stoch 15, Chumai, Peng, and Zoller gave a very nice result that extends to general values of k. So it just is not restricted to k equals 1 versus 2, so say 1 expander versus 2 expanders, as in the classical work of Goldreich and Ron and the follow-ups, but rather handles a general k. So they show that how to solve the problem in roughly n to the 1/2 times poly k time. Think of this as basically testing what is k. However, there's a downside here. They need a very good clustering for their techniques to work. In particular, what they do only works when epsilon is inverse polynomially small in the number of clusters and scales as 1 over log n. N is the number of vertices in the graph. Good. So in a paper with Ashish Chiplunkar, Sanjeev Khanna, and Aida Muzaffar, and Perez, in Fox 18, we showed how to do testing for any epsilon smaller than a constant in time n to the 1/2 plus order epsilon times poly k factors, and we proved that this is information theoretically optimal. That is, specifically, we proved that distinguishing an expander between an expander and a graph that is 2 omega 1 and epsilon clusterable requires at least n to the 1/2 plus omega epsilon accesses to the graph, and hence this gives a lower bound on the runtime. Okay, good. So this is the prior work. Note that our previous result with Chiplunkar, Khanna, Muzaffar, and Perez solves the testing version of the problem all the way up to the information theoretic limit, namely up to epsilon being a small constant, but it does not really provide a fast query access to the clustering. And so this is what we want to do in this talk. Great. So before I tell you how we do it, let me spend some time talking about how one could imagine approaching this. A very natural approach to this problem is the idea of spectral partitioning. So it's a very popular method for partitioning graphs. Here is what we would do if we were to do spectral partitioning. The first thing we would do is compute the eigendecomposition of the normalized Laplacian of our input graph, G. Great. So once this is done, we essentially have an embedding of the vertices of the graph into Euclidean space. So what is this embedding? We'll simply look at the bottom k eigenvectors, or the ones corresponding to the smallest k eigenvalues of the normalized Laplacian. And well, these are each of them is a vector of length n. So every vertex can now be associated with a k-dimensional vector. So this embeds vertices of the graph into Euclidean space. And then this essentially reduces the problem to a Euclidean clustering problem. Basically, what we hope to see is k-tight clusters of points, and such as what we see on this picture. So what we see on this picture is actually the result of taking a 3-clusterable graph. It's a random Erdős-Rényi graph, and then embedding the vertices of the graph using the second and the third eigenvectors of the Laplacian, just to have a 2-dimensional picture. After all, the bottom eigenvector of the Laplacian is just all ones, so it's not very informative. And indeed, as expected, we do see 3 good clusters. Great. So what is the problem with this approach? Well, from our perspective, the main problem with this approach is that this is very expensive. Although, in fact, one should also be careful analyzing the precision here. So we do not want to compute the eigen decomposition of the entire graph Laplacian, and instead we would somehow want to access this eigen decomposition in sublinear time. Okay, this is the task. Great. Well, for this purpose, it seems reasonable to revisit the techniques that were designed in the sublinear algorithms property testing literature for the problem of testing the number of clusters. And here the idea is to think about, is to somehow try to use the distributions of short random walks in the graph as proxies for the spectral embedding. So let me denote by M the random walk transition matrix of our deregular graph, and we'll use lazy random walks to make sure we don't have any issues with bipartiteness. So that way, for a vertex x in the graph, m to the t times 1 sub x is the distribution of a t-step lazy random walk started at x. So here t is the length of the walk that we run. Remember that our clusters are assumed to be omega-1 expanders. So the walks that we run will be logarithmic length. Basically, this is the length that ensures that the walk inside a given expander mixes to the stationary distribution to some inverse polynomial precision. Okay, great. So basically, we would like to understand how much information one can glean from the distribution of t-step walks from vertices in the graph. Great. So here's a very nice approach that was introduced by Chumai, Peng, and Zoller in Stoch 15. This was for the testing problem of distinguishing whether the input graph is actually k-clustering. Their algorithm is basically this. Well, we first sample a subset S of vertices in our graph. And how many vertices do we sample? Well, we sample at least k, or just some polynomial number in k of vertices. The hope is to just hit every cluster a representative number of times. Good. And then one constructs a sort of a similarity graph, call it H, on the sampled vertices, where we connect vertex x to vertex y if and only if the Euclidean distance squared between the t-step distributions of random walks is at most a small constant divided by n. So there's some threshold, and you basically just connect two vertices if the distributions of their random walks are close in Euclidean in L2 squared, and you don't connect otherwise. And then they say that graph G is k-clusterable if and only if this meta graph that we create on the sampled vertices is a union of k-cliques. Okay, good. So this is a very nice approach. And indeed, this gives a sublinear time algorithm. Why? Well, the not obviously sublinear part here is this computation of Euclidean distances. And indeed, you can't really compute them exactly in sublinear time, but you can check this condition in about square root n time, basically by doing collision counting. You run about square root n random walks from both vertices, and you check if you have enough collisions. So if you have enough collisions, then they're probably close, and if you don't, then they're not close. All right, good. So this works, but this only works when the clustering is extremely pronounced, namely when epsilon is at most inverse polynomial in k and at most 1 over log n. Good. So why is that the case? Well, basically, one can observe that if the clustering is so pronounced, that is, epsilon is much smaller than 1 over log n, then basically the distributions of short random walks are just a very good proxy for the spectral embedding of the graph. And let me illustrate this by picture. So here's what I did for this picture. I took a random three clusterable graphs, which is 3 expanders with a few connections wired across. And what I do is, first on the left, I plot the spectral embedding. Just every vertex is mapped to its position in the second and third eigen vector of the normalized Laplacian. And on the right, what I do is I basically just I plot the vertices. I plot the corresponding random walk-based embedding. and really, I did not define this on the slide, but what happens is along every coordinate direction, and in this case there are two, the second and the third eigenvector, there is a certain scaling introduced by the random walk. So the longer the walk, as you change the walk, the right picture changes because epsilon is not that small, and when epsilon is very small, then it doesn't matter how long you walk for, at least up to 1/log n, the picture that you observe is pretty stable and basically just corresponds to the spectral embedding. Okay, great. So basically it turns out that it is not really possible to do a clustering of k omega of our clusterable graphs all the way up to the information theoretic threshold, namely when epsilon is merely a small constant, using these distance-based ideas. And hence we need to design some new techniques, and this is exactly what we do. Right. So just to reiterate, the problem here is the following. Basically, ideally, we would somehow like to get access to the spectral embedding of the graph. Instead, we get access to the random walk-based embedding. And intuitively, this random walk-based embedding is the following object. A vertex x is mapped to the t-step distribution of the random walk started at x. And one can verify that this distribution is basically this. It's the spectral embedding, except every coordinate is distorted according to the corresponding eigenvalue. Since we don't know these eigenvalues, this is a problem, and intuitively we somehow want to get rid of this scaling along various directions.
What
good.
You here, Michael? Can you just?
Oh, okay, good. Yeah, so let me perhaps stop here and check if there are any questions. Yeah,
yeah, just so U2 and U3 are the eigenvectors. What is U2 of x? It's just the projection.
Good. Thanks. So yeah, so here U1, U2 through Un are the eigenvectors of the normalized Laplacian, right? And so what is the spectral embedding actually? What is the spectral embedding of x in the case of a three clusterable graph? It's actually when x is mapped to a three-dimensional vector, u1 of x, u2 of x, and u3 of x. That is, like u2 of x is just the xth coordinate in the second eigenvector of the Laplacian.
Okay.
Right. So u3.
So you treat these like the bottom k or the bottom 2 in this case as the as a basis, and then the coefficients for 1x is u2 of x. Is that
exactly? No,
okay.
wait. Is it exactly so? Can you repeat the last?
You look at u2 and u3 and you express the characteristic vector of vertex x as a sort of a linear combination. The coefficients are u2 of x and u3 of x.
Okay, I'm not. I wouldn't entirely subscribe to this. Let me just phrase it slightly differently. Just think of taking a vector x. You take a vertex x and you map it to a point in 3D space, where the first coordinate is u1 of x, the second coordinate is u2 of x, the third coordinate is u3 of x.
Okay.
That's the spectral embedding. So just imagine having your three bottom eigenvectors as three rows of a matrix, right? And then, or let's say three columns of a matrix, and then the x is the spectral embedding of x is the xth row. So it's a vector of length 3. Yeah.
Okay. Yeah.
Good. And good. So basically, what is the point that I'm trying to make here? The point is that somehow we do know how to cluster graphs. We have techniques for clustering when we can access the spectral embedding, and we basically just compute the embedding first, and then we sort of apply some Euclidean clustering on the embedding. But now we don't really have that access, right? However, we have access to what we do get to do is we get to take a vertex x and run a logarithmic length random walk from it. So that way, we can associate with a vertex x the distribution of a logarithmic length walk started at that vertex. And we hope that this distribution is kind of close to the spectral embedding. And this hope is warranted. This is exploited in previous works. However, it turns out to not be close enough. That is, if you have a very pronounced clustering, basically this epsilon is very small, say smaller than 1 over log n, then the distribution of the random walks is of a log n length random walk is basically the spectral embedding. However, we want to go way beyond that. We want to go to the regime where epsilon is merely a small constant, and in that regime, somehow the spectral embedding is, the random walk-based embedding is kind of the spectral embedding with some unknown scaling because of these eigenvalues. Yeah, I'll talk about that later. Good. So good. So these are the prior techniques, right? And let me get to our main result. Right. So again, let me formally define the spectral embedding for you. So here, let u1, u2 through un be the eigenvectors of the normalized Laplacian of our graph. So here they are stacked in a matrix. So let's say for the 3-clusterable graph, you see 3 columns of this matrix, u1, u2, and u3. And then the rows of the matrix are indexed by vertices in a graph. So for every vertex x in V, the spectral embedding of x is denoted by f sub x. And this is nothing but the xth row in this big matrix. Okay. And the main question that we would like to ask is basically whether we can somehow access this spectral embedding in sublinear time. Basically, we want to avoid computing an eigendecomposition, computing an SVD, or really an eigendecomposition of the Laplacian of the graph. But we want to access this embedding in time much less than n, so without even looking at the entire graph. All right, so this question, as stated, is actually a little bit ill-defined. So let me, why is it ill-defined? Well, for example, it's ill-defined because these eigenvectors, u1, u2 through u3, are not really well defined. In the presence of repeated eigenvalues, there are many choices for the spectral embedding. So, however, what is true is the following, that for every k omega 1 epsilon clusterable graph, while the eigenvector, the bottom k eigenvectors the same are not necessarily unique, the space spanned by them is. And this is because there is a gap between the kth and the k plus 1th eigenvalue of the Laplacian, of the normalized Laplacian. So the real question that we want to ask is whether or not it's possible to get dot product access to the spectral embedding. That is, I want to design a small space data structure that, given 2 vertices x and y, will quickly compute the dot product between the embedding of x and the embedding of y for me. Are there any questions about this? About this thing? Oh, and by the way, Anand, how much time do I have? I have 50 minutes plus questions. Is that correct?
Yeah, so we have around 25 minutes left.
All right, great. This is good. Okay, so this brings us to our main result, right? And we basically show that there exists a data structure that can approximate these dot products, fx in the spectral embedded space, up to additive error, up to some small additive error, in time n to the 1/2 plus order epsilon. So there are some details on this slide, but really the way to read it is that if you have a k omega 1 epsilon clusterable graph for some small epsilon, then it is possible to get dot product access to the spectral embedding in n to the 1/2 plus order epsilon time. So this dot product access has some additive error, and the additive error is specifically some precision parameter gamma divided by n, and we're polynomially dependent on this precision parameter gamma. But just let me say that this is the right amount of additive error. This is because for a typical vector, fx, the length of a typical vector in the embedded space is about k divided by n, the length squared. So really, this is the amount of additive error at which you start getting non-trivial results, and as I will show, this suffices for clustering. Good. Okay. One should also note that one can get some trade-offs between query and pre-processing time, but mainly think of this as n to the 1/2 plus order epsilon query time algorithm for getting dot product access to the spectral embedding. Good. So fantastic. How does that help us cluster k-clusterable graphs? That is, remember that my main goal was to get a spectral clustering oracle. Good. Well, indeed, this turns out to be possible. So we show that using this spectral dot product oracle, one can get a spectral clustering oracle with misclassification error order epsilon log k. So remember, I was hoping to get order epsilon. We don't know how to do that, but we lose a log k here, but it's pretty close to the best possible. So here the pre-processing time is n to the 1/2 plus order epsilon times some factors that exponentially depend on k, the number of clusters. I'll say a few words about this in what follows. The query time is a polynomial in k times basically n to the 1/2 plus order epsilon. Okay. So note that this is essentially information theoretically optimal due to our previous lower bound showing that even distinguishing between one clusterable an expander and two clusters with outer conductance epsilon requires n to the 1/2 plus order epsilon queries. Any questions about the statement of the result? All right, good. Good. So in particular, so here one can also get some trade-offs between query and preprocessing time as well, and as a consequence, one can Great. So in the remaining time, I will say a few words about the actual techniques. And I will do this in the opposite order. So I will first assume the ability to compute dot products in the embedded space up to appropriate error in sublinear time, so in n to the 1/2 plus order epsilon, very quickly. And I will talk about how this implies a good clustering algorithm. And then I'll say a few words about the construction of the actual dot product oracle. Good. Okay, so basically, suppose that we have sort of full access to the spectral embedding itself. How would one actually go about clustering the graph? Well, the basic intuition, as alluded to before here, is that we hope that in the embedded space, the vertices in the graph basically form k reasonably disjoint clusters. So say in the case of a 3-clusterable graph depicted on the slide, we hope to see 3 pretty tight clusters. Okay? Good. And to some extent, this is indeed true, but there are some details here. So what is hence, in order to do clustering, it is very natural to first define the notion of cluster centers in the embedded space. What are those? Well, if I have a cluster C, then its center nu is nothing but the average, over the vertices in the cluster of their spectral embedding. So here on the slide, I have mu1 is the center of the red cluster, mu2 is the center of the blue cluster, mu3 is the center of the green cluster. Good. So now we would like to prove a claim. Right? We would like to prove some claim that supports the intuition that in the embedded space, we should see 3 fairly disjoint point clouds, and then we declare those to be clusters and hopefully solve the problem. So what is the formal claim that provides such a statement? So this is something that we call the variance bound. The variance bound says the following. It says that if we let, so here's the bound as shown on the slide. Basically, it bounds the amount of variance that the points have around their mean in any direction in this k-dimensional space. We specifically choose any direction alpha in Rk, just a vector of unit Euclidean norm, And for every vertex x, let mu sub x be the center of the cluster of x. If the following bound turns out to be true, if you sum over all vertices in the graph, what do you sum? You look at the difference between fx, the point at which fx is embedded, and the cluster center mu x, and then you project this onto direction alpha, and sum up the squares of those things. This is small. So this is order epsilon. This is roughly the outer conductance of our instance. Okay. So basically, one can bound the total square deviation of the embedded points from their centers in any direction in this k-dimensional space. Good.
All x in what? Over all x in the graph.
Yeah, exactly. Good. So here the sum is over all x in the graph, right? And so note that what you're doing is you're looking at the distance from fx to its corresponding cluster center. So this is a vector. You're projecting this vector onto your favorite direction alpha, and you're summing the squares of these projections.
Yeah, thanks.
Good. So using this, so this you can prove. I will not talk about the proof much, but maybe one sentence is this follows by basically noting that the quadratic form of the Laplacian on a corresponding linear combination of eigenvectors is small, and then noting that these clusters are expanders, and the Laplacian of a deregular, the normalized Laplacian of a deregular expander basically computes the variance of the input vector. So these two facts put together can be shown to imply this bound. Okay, great. So from this bound, you can also show that these cluster centers are actually nearly orthogonal in the embedded space. And their Euclidean length squared is roughly equal to 1 over the corresponding cluster size. All right, good. So this is somehow done by essentially rounding the spectral embedding matrix. Good. So equipped with these facts about k-clusterable graphs, so somehow quantify the amount of concentration of vertices around their corresponding cluster centers, let's design a clustering algorithm. And let us just assume that we know the cluster centers, mu1, mu2, and mu k. In reality, we don't, but we will guess them later. And this is actually why we get this exponential dependence in the runtime on k. We enumerate over all the possible cluster centers. Good. So suppose we know the cluster centers, and we want to design clusters, partition C into Ci tildes. These are approximate clusters such that every Ci tilde is a good approximation of the corresponding cluster Ci. Great. So here is a very natural proposal. Let's do hyperplane carving. What does that mean? So for every I define Ci tilde to be the set of vertices on the graph that are pretty correlated, say 0.9 correlated, with the corresponding cluster center in the embedded space. So just compute the dot product between fx and mu I, and compare this to the length of the corresponding mu I. Of note that this is good because I want a clustering algorithm that only uses dot product access to the spectral embedding space, which I have by my dot product oracle, and this indeed can be done at least approximately using this dot product oracle. So here's the pictorial representation, right? We just cut off the corresponding clusters using hyperplanes. Okay, so indeed, this is not a bad idea. One can prove that if we define these clusters Ci tildes in this way, then every individual cluster Ci tilde will indeed be an order epsilon approximation of the corresponding Ci. Great. However, there is a problem, and the problem is that these Ci tildes into Ci tildes such that elements in the partition approximate the original cluster as well. Good. So here's an example why they can overlap. It's an interesting example. Suppose that we have a 3 clusterable instance, And so here's the spectral embedding of this instance. Now, the following configuration is perfectly consistent with our variance bound. The configuration is the following. So clusters mu1 and mu2, the ones at the bottom, are not very interesting. They're just some natural point clouds with variance that is matching the variance bound. But the third cluster is funny. It basically has an epsilon fraction of points deviating in the two orthogonal directions, mu1 and mu2. So the problem with this is that once we do hyperplane carving on mu1, we take a chunk of this cluster mu3. And once we do a hyperplane carving on mu2, we again take a chunk out of this cluster mu3. And this is the real problem, because one can construct examples that are perfectly consistent with the variance bound, where you can, if you do hyperplane carving on, say, k-1 clusters, each of them will take out a 1 over k fraction of the last one, and so you don't even get k clusters in your solution. Okay. So what is the fix for this? The fix for this turns out to be the following. We redefine the approximate clusters Ci hats as follows. A point x, a vertex x, will belong to the ith cluster, the ith approximate cluster, only if it is pretty correlated with the ith direction and not correlated with any other directions. So that way, by definition, these Ci hats do not overlap, and that is great. Okay. However, the problem with them is that they don't necessarily form a good clustering, because let's say in this example on the slide, this cluster Ci hat, C3 hat, the green one, was damaged non-trivially by the first cluster and the second cluster. Say, one can easily construct examples where, for all we know, just a constant fraction of this cluster will remain, and that is not good. However, it turns out that one can do the following. For clusters defined in this way, we can check which ones have small outer conductance, and one can verify that those will then match the corresponding original cluster as well, and take those out. It turns out that at least a good constant fraction, let's say half of such approximate clusters, will be good. So at most, a half of the clusters will be damaged. So just like in this example. So what do? We look at the good clusters, look at the Ci hats that are good. We declare them to be good approximations to the Ci's, and we recurse on the space orthogonal to the space spanned by their centers. So for example, in our instance on the slide, what we would do is we would first discover clusters, the red and the blue cluster, after which we project out the corresponding two dimensions and recurse only on the vertical dimension. And as we see, indeed, these deviations, the deviations that we observed, were deviations in directions 1 and 2, but not in direction 3. And we get a good solution. So there's a certain recursive process here that proceeds over log k steps, because at every point we recover a constant fraction of the clusters that we currently have, and hence we incur this factor log n loss in the outer conductance. Okay, great. So good. So one thing to note here is that our variance bounds are perfectly compatible with the idea of recursing on subspaces. Right. This is because the variance bound was applicable to any direction alpha in our RK. So this just goes on, seamlessly applies to subspaces. And the main idea is that while in general the original distribution of points around cluster centers may not be as concentrated as we would like, these deviations cannot concentrate on low-dimensional subspaces, and which is why this process of peeling over a logarithmic number of steps succeeds in recovering every cluster, as opposed to a good fraction of clusters. Okay, so I don't have that much time, so let me just say a couple of words about the actual dot product oracle. I do have still 5 minutes. Is that correct, or maybe 3? Anand, is that accurate?
Yeah, we have around 5 minutes.
Okay, great. So then I can say a few words here. Good. So what is the goal here? Basically, let u1, u2 through uk be the eigenvectors of the normalized Laplacian. The lambdas are the corresponding eigenvalues. So this is shown on the slide. So the eigenvectors are the columns. And we let fx be the xth row of the corresponding matrix. So now, given two vertices x and y, we want to quickly estimate the dot product between these two rows. What is quickly? Quickly means in time less than n, so n to the 1/2 plus a little bit. Great. Good. So what we know is that instead of doing the dot product between these two rows, we can definitely approximate well the dot product between the distributions of t-step walks out of these two vertices. And this is again by the Bernoulli paradox, collision counting. Great. So let me just write the formula for the expression for the corresponding dot product on the slide. Now you can express this dot product in the spectral domain as follows. It's basically the dot product that we're interested in, except that we're summing over all eigenvectors i from 1 to n. And instead of just summing the products, we also have these scaling factors, 1 minus lambda I by 2 raised to power 2t. So this factor 2 is actually because of the lazy random walk. Good. So first, in the random walk, we sum over n eigenvectors, but not over k. Well, that is not a problem because the k plus 1th eigenvalue of the Laplacian of a k clusterable graph is large. So basically, the other terms are inverse polynomially small. They vanish. So the sum is really pretty much over k terms, but these scaling factors, they are a problem. They have been a problem all along. So essentially, we need to somehow learn how to divide by them. Right. Good. So how do you divide by these scaling factors? Well, basically, instead of doing the approximating the dot product between the distributions of random walks, we need to inject a certain matrix, which will divide by a corresponding matrix. And here's this matrix. It's some sort of a sum of outer products of bottom k eigenvectors with appropriate scaling factors. Now, of course, we don't know this matrix, but it turns out that we can estimate it. So how do we estimate this matrix? Well, what you do is you take a smallish number of samples of vertices from the graph, call this S, it's poly k times n to the epsilon or so, and then approximately compute the gram matrix of t-step random walks out of these vertices. This matrix you can compute efficiently using collision counting again. And then you look at this matrix, you compute the eigendecomposition of this matrix. You truncate this eigendecomposition, you basically do a rank k approximation of that, and you divide, so to speak, divide by this matrix in the middle. I don't have time to get into the details of this. Let me just say that the proof relies, the analysis of this algorithm relies on matrix perturbation bounds, such as the Davis-Kahan sine theta theorem. We essentially prove that in k clusterable graphs, you can get a very good approximation to the bottom, to the eigenspace spanned by the bottom k eigenvectors of the Laplacian, and that's how this proceeds. One interesting thing to note is that in the process of one of the useful tools for the analysis that we developed is essentially an upper bound on the leverage score, on the leverage scores of the rank k approximation to this gram matrix of t-step walks, really to the matrix of t-step walks. What we prove, and this is very useful in the analysis, is that for k clusterable graphs, somehow the spectral embedding into the bottom k eigenvectors has fairly low variance. So I'll say the L infinity norm of the bottom k eigenvectors of such graphs is nicely bounded. This may have other applications elsewhere. All right, good. So this is what I have as a summary, as we showed how to design spectral clustering oracles with order epsilon log k error per cluster, and that this runs in n to the 1/2 plus order epsilon time, at least for up to some lower order terms. There's a lot of exciting questions here. Very direct ones are, can we get polynomial dependence on k, sort of avoid enumerating over the candidate cluster centers? Can we be sublinear? Right now, we are sublinear for small enough k. And generally, I think it's a very interesting question whether one can use this idea of getting dot product access to the spectral embedding somehow beyond graph clustering, so maybe in some latent Dirichlet models in more complicated but still well-structured settings. Okay, so this is it, and I'd love to take any questions. Thanks a lot for your attention.
Okay, thank you, Michael, for a great talk. So are there any questions?
Yeah, just a sort of a quick question, Michael. So if these are like for the testing problem, this is life is much easier, right? You would like probably all of this is a sort of a fairly subsumes like whether there are K clusters and so on. So you won't even have to probably like even. So I'm just trying to understand how things would become simpler if the goal was just to test whether the cluster.
Yeah, great question. So basically, yeah, so this is good to look at our previous, this Fox paper with Khanna, Chiplankar, Perez, and Muzaffer. But basically it is easier because there we show that if you want to test, all you need to do is this. You need to just you sample a few vertices and you look at these t-step distributions. So now you map vertices to vectors, t-step distributions, distributions of the t-step walk. Then you look at these vectors and you ask yourself, are these vectors, do they span a non-trivial k-dimensional volume or do they not? That is, if your graph is, can be partitioned into less than k clusters, then the k-dimensional volume of these vectors is like very small. Specifically, you just look at the Gram matrix of these walks and you compute the k+1 eigenvalue. Right? And that eigenvalue, if the graph has fewer than k clusters, will be inverse polynomially small, like 1/n^20. If the graph has at least k clusters, then that eigenvalue will be non-trivially large, like at least n to the minus order epsilon or so, just because we have the sparsity condition. Yeah, exactly. So it's very interesting because there you just look at the volume, you need sort of very crude access to the spectral embedding. Right. Whereas if you want to actually cluster, that's why we started to sort of undo these multiplicative factors that have to do with eigenvalues. That seems necessary, but for testing you don't care.
So in a sense, you don't need to know K a priori. Like if the promise is it is clusterable for some value of K, you can probably like do a binary search and like.
Oh yes. Yeah, exactly. If you give me an upper bound, if you promise to me that it's K clusterable for some K at most K star, then what I will do is I will just sample poly K star vertices, look at the Gram matrix, and look at the eigenvalues of this matrix, and check how many largish ones I have, and that will be the K.
And one final question. So for let's say if I look at the planted version of this question, where the cluster, like there is each cluster has sort of a high probability of like inter-cluster connectivity versus like intra-cluster connectivity. Does like some parts of it simplify, or is it still?
Oh, I see. You're saying what if we look at the stochastic block model, basically, that these are not worst case expanders? Yeah. I see. Great. So I haven't. Yeah. So this is very interesting because I don't know how to simplify because I haven't really thought about it hard enough. But what is very interesting is that even the thresholds for recovery change. For example, in the stochastic block model, like here, we show that you basically need time n to the 1/2 plus omega epsilon when your outer conductance is about epsilon. That is essentially if you unless you have a sublinear fraction of edges going out of your cluster, you can't really recover, and formally the runtime will go up, right? However, in the stochastic block model, a very different thing happens. There you can information theoretically recover even when your outer conductance is really bad, basically because if you have like k clusters, all in all, you can still recover if the probability of an edge inside to your own cluster is somewhat smaller than the probability of an edge to the outside. But that means that you're still recovering even when the fraction of edges going out is a factor k or so bigger than fraction of edges going to your own cluster. So things really change there. Basically, in the random setting is much more structured. It's a very exciting question, I think. Basically to check what are the sublinear recovery thresholds for these random planted models, as you say. Yeah, I don't know. It's very interesting.
Okay, but yeah, I'm curious too. Yeah. Okay. Thanks.
Yeah. All right. Good.
Okay, are there any other questions? So in your talk, so earlier you mentioned that you're assuming the vertex degrees are bounded. So where is that being used?
Oh, I see. Good. Where is the upper bound on vertex degrees being bounded used? Yes. So good. Good. Even good. So for good, let me answer it like this. The testing result that I mentioned, our previous results on this problem, we could actually make work even for graphs with unbounded degrees. So there we had a sort of square root m of the number of edges runtime, which I think should somehow be improvable, but anyway, that's what we could get. And just to outline the differences, for example, even, yeah, like, you would need to normalize, basically you would need to normalize by inverse degrees in various places. And for instance, so whenever we say we sample a few vertices, you would need to presumably sample with probability proportional to the degree. So all in all, I would think that it should generalize to, I'd be surprised if there are serious obstacles to generalizing this result to giving m the number of edges to the 1/2 plus order epsilon runtime for general graphs. And yeah, that would be nice, but what I don't know how to do is somehow how to keep the runtime square root n, even for unbounded degree graphs. I don't know why it's not possible. I think it's just that we probably had a weaker analysis. We sort of ran out of energy at that point for the previous paper, and for simplicity, we did this one in the degree debounded case. It would be very nice to work this out. Should be doable. But I would, yeah, let's probably start with testing.
Okay, there are no other questions here. Let me stop the recording so that we can have a more informal discussion after this.